Okay, let's look at the next example. Example 10.4. Okay, the problem stay like this. So this is also a pipe, 1,000 meter long, 0.2 meter diameter, and the total loss of this 1,000 meter pipe, the total loss is 12.2 meter, total frictional head loss. Viscosity is the same as the previous problem, 1 by 10 to negative 6 meter per second square. Meter square per second. What is the flow rate? So the question. So the material is also asphalted cast iron. Okay. So what is the flow rate? To calculate the flow rate. Very practical problem actually, right? So what do we do? So what's the first step? So which case is this, right? Which case is this? This is dictates our procedure, right? So we are asked to calculate the flow rate. So it must be case 2. Okay, but case 2 has 2 subcases, A and B. Depending on do we have HF or not, right? The friction head loss. For this problem, we have the HF, 12.2 meter. So it belongs to case 2A, okay? Case 2A. So let me show you how to solve problem for case 2A, all right? So obviously, this problem we are calculating flow rate. Basically, is flow rate means velocity, right? Because we know the diameter, we know the cross-sectional area. So flow rate basically is just velocity times the cross-sectional area. So our goal is to find the velocity. Obviously, in this Darcy-Weisbach equation, we have the velocity, right? We want to try starting from there. So HF equals to FL over dV squared over 2G. Okay, so putting everything we know, 12.2 meter HF equal to F times 1,000 divided by 0.2, right? Then times V squared over 2G. Okay, so in this equation, obviously, we have 2 unknowns, F and the V. So we need to figure out F before we can calculate the V, right? So friction factor, this is the case 2A. So we are going to use Moody diagram, right? And we are going to use the top axis of the Moody diagram. Okay? So the top axis of the Moody diagram is this, d to the order of 3 over 2, and square root of 2g hf over L over viscosity, right? We have everything, right? Diameter is 0.2, G, we have HF is 12.2, L is 1,000 meter, viscosity is given. So the top axis is 4.38 times 10 to the 4. Okay, so in Moody diagram, we also need the right axis, which is relative roughness, is same as the previous problem. So it's 0.0006. So you have the right axis, you have the top axis. So from Moody diagram, we can find our F is 0.019. Okay, then substitute F into this expression, this equation. We can calculate V, velocity 1.59 meter per second. Then the flow rate will be V times quarter pi d squared, so equals 0.05 cubic meter per second. Okay, so this is example 10.4. Now let's look at example 10.5, another example here. Okay, 10.5 is look like this. Okay, you have a reservoir. The surface is 60 meter. Okay, there's a pipe outlet, 100 meter long. Okay, the flow exposed to the atmosphere. The diameter is 0.5 meter. The material is steel for the pipe. Material for the pipe is steel. At the outlet, the elevation is 40 meters. So you have a 20 meter elevation drop, right? So for this problem, what is the Q? The flow rate in the pipe. Okay, this is also a very practical problem. To calculate the flow rate from the reservoir, okay, with a pipe at the outlet. So which case is this? Of course, 2, right? Case 2, A or B? HF is not given. HF is not given. It has to be case 2B. Okay? We are not going to use the top axis of the Moody diagram because we don't have the HF. Okay? Not able to. So case 2B, we have to use iterative procedures. Let me show you this procedure. Okay. So for this problem, obviously, energy equation in the pipe, we're going to start with that. Okay. Specify the location 1 and 2. Obviously, on the reservoir surface is 1, at outlet is 2, right? We can write down the energy equation in the pipe, which is similar to Bernoulli equation, right? It's energy equation in the pipe system, right? P1 over gamma Z1, V1 square over 2G equals P2 over gamma plus Z2 plus V2 square over 2G plus the loss. We can have the loss expression here. Okay, here in chapter 10, we know the expression for the frictional head loss. So let's leave it, put it in there, FL over dV square over 2G. So what kind of V are we talking about? It must be V2, right? Outlet velocity is the same velocity in the entire pipe. Okay, let's simplify it. P1, P2 is 0, open to surface. V1 is 0 on the top of surface and no velocity. So 60 will be equals to 40 meter plus 60 meter equals 40 meter plus, okay, C2 is 40 meter, right? V2, we don't know, right? We are going to find out V2, okay? So let's use V to represent V2. There's only one V here, so we don't need to do V2, just say V. Okay, let's group the last two terms together, Okay, V square, both have V square over 2G, right? So it becomes 1 plus F times L over D, right? Then parentheses, right? Then times V square over 2G, okay? So this is an equation with two unknowns. Again, similar to the previous problems. They have two unknowns in this equation, F and the V. So we can rearrange this equation a little bit, calculate a little bit, rearrange it. It becomes a form like this. V equals to 2G times 20 divided by 1 plus 200F. Then take the square root of the whole thing in the right hand side, right? That's from, this is just a little bit. We group the terms a little bit, rearranged it into this form. Okay? So next, what should we do? We have two unknowns in this equation. We are not going to directly find out F. If we can find out F like previous problem, we can find out V immediately. But no way we can use Moody diagram directly to find F because we don't know the velocity, then we cannot find the Reynolds number. So bottom axis of the Moody diagram is not possible. And we don't have the HF. So the top axis of the Moody diagram is also not possible. Okay. So what we do is here, I put the procedure in this side. Okay, iteration method. So we start with a guess value of F. So you have two unknowns, F and the V. So you will guess one of them. Okay, let's guess F. We probably know the range of F more than V, because F probably is in the range of 0.01 to 0.03 in that range, right? It won't be too, if you look at the Moody diagram, it won't be too far away from the 0.1, 0.01 and 0.02. It should be in between. Okay, so it's a little bit easier to guess. If you guess velocity, I totally have no idea. Velocity could be 1 meter per second, could be 100 meter per second, could be 1 inch per second maybe. So you don't know, you have no idea. So F is a little bit easier to guess. Okay, so but initial guess is okay. We're gonna iterate. So eventually the good solution will replace the guess the solution, right? So we guess 0.02 for F. So based on this equation, based on this guessed F value, you can calculate a velocity. Okay, so velocity based on this F equal to 0.02, velocity is 8.86 meter per second. Okay, now with the velocity, that's a little bit easier. With the velocity, now we can calculate the Reynolds number. Okay, we know the diameter, right? We know the viscosity, so we can calculate Reynolds number. With the surface roughness, which is a steel pipe, right? From the table, we can find the relative roughness, 9.2 times 10 to the negative 5. Okay, so with Reynolds number and the surface roughness, bottom axis and the right axis of the Moody diagram, we can find our F. Okay, equals to 0.012. Well, it might not be the final answer yet, but it's better than the initial guess, I guess, right? So now you have a new F value, okay? With this new F value, you can use this equation again to find a newer V value, velocity, 10.7 meter per second. Okay, a little bit better ones. Okay, that's the same procedure following step 1, 2, 3, right? After 4, I put down the step 2 again because that's repeating the process, right? So then Reynolds number based on the new velocity and the surface roughness is the same. So you can go to the Moody diagram again. Now the F is still equals to 0.012. That's little change of the Reynolds number doesn't change the F value much. Okay. So now, do you think we need to stop here or continue the iteration? You don't need to, because now you with this new F 0.012 same as the previous one. If you substitute to that equation, the velocity is still 10.7. You get still same Reynolds number. You will have still the same F value. That means the F value converged. That's a big word, converge, okay? If you do inter-iteration, you will try to reach a converged solution, okay? Here we reach the converged solution, F equal to 0.012. That's the final F value. So now we substitute into F, into the equation, the velocity is 10.7 meter per second, then your flow rate is velocity times the cross-sectional area is 2.1 cubic meter per second. Okay, so this is the problem for case 2B. Okay, the iterative method to determine the flow rate. Very important. Okay, another example 10.6. Okay, this is a pipe design example problem. Okay, so the design criteria are listed here. Okay, so you need to meet these requirements. So the material for your design is asphalted cast iron. Okay, the required flow rate 3 cubic feet per second. Okay, your head loss, required head loss 4 feet. That's your design spec, right? The length, okay, of course, length we need to give you, right? So the length is 1,000 feet. Okay, so what is the diameter? So you design the piping system for this case, right? To have the flow rate 3 cubic feet per second, to have a loss 4 feet, 1,000 feet long. What should be the diameter? Okay, it's a very practical design problem. So viscosity is given 1.22 times 10 to the negative 5 feet square per second. Okay, for the asphalted cast iron, the K, the surface roughness, is 0.005 inch. Okay, so what is the diameter? Okay, so that's the problem. So which case is this? Obviously, this is the case 3. Case 3 to find the diameter. Your unknown is diameter, right? So do we have everything? We have everything we need. Flow rate, length, and head loss. Okay, we need these. So it should be good. We should be able to solve this problem using a iterative method. Okay, so let's go through it. So you use Darcy-Weisbach equation for this. Diameter is there, so we will start using this equation, right? HF is given, right? Is 4 feet, which is equals F times 1,000 length over D. D we don't know. V square will be Q divided by A square, right? Q square divided by A square. It's flow rate divided by area divided by 2G. Okay, so if you rearrange it a little bit, you can put in the value a little bit. It will be like this. Q is given, area is quarter pi d square. So area square will be quarter pi square d to the power of 4, right? Okay, so the total HF equals 4 feet, right? The whole thing, this expression equals 4 feet. So you have two unknowns there, F and the D. D to the power of 5 total. You have one D here under 1000, another D to the power of 4 in the last term. Okay, so you have F and the D as unknown. No way, again, without D, no way you can directly use the Moody diagram. Either top axis and the bottom axis both need D. You don't have D, you don't know the value. So in that sense, you cannot get F directly from the Moody diagram. We have to use iterative procedure, just like a previous problem. So if you rearrange this equation, it will become D to the power of 5, okay, equals 56.7 F. Okay, so your D and F are two unknowns. Okay, the whole thing HF is 4 feet. Okay, so if you rearrange that equation, become this. This equation have two unknowns, right? If you have two unknowns, we can use iterative procedures. Again, well, we will have a guess value for F first. Again, we have no idea of diameter. It will be better to just guess F. It won't be too far away, right? If you guess an F value 1 million, then it will still get you the solution after maybe 1,000 iterations, right? You want a limited number of iterations, so you have a better guess. It will be better. So let's guess F equal to 0.015. Again, F most of the time is between 0.01 to 0.03. Okay, so 0.015 for F. So based on this equation, D can be calculated 0.968 feet. Okay, so with the knowledge of V, we should be able to calculate our velocity, right? Eventually, we're going to use Moody diagram, bottom axis. So velocity will be flow rate divided by cross-sectional area. We have a D now, right? So you have cross-sectional area. So our velocity is 4.08 feet per second. With that, you can calculate the Reynolds number. The Reynolds number needs a D, right? So also the right axis, relative roughness need a D too. It's now this time when during the iteration, the K over D also changes every time because D changes, okay? So the K over D relative roughness will be 0.00043. Okay, so with that, from Moody diagram, F equals 0.0178. That's a better F than the initial guess. With this better F, you find your diameter 1.002 from the equation. Okay, repeat the process. Velocity based on that, based on this diameter, 3.81, Reynolds number, then roughness, relative roughness. Now you have a new F equals 0.0178. Oh, okay, that's exactly the same F. So you don't need to continue to do the iteration. You can stop here. The solution converged. With this F, your velocity is 1.002 feet. Okay, you already calculated here, so it won't change. So that's your designed diameter. Okay, so this is a very practical problem. Very practical problem. In piping design, with this problem, actually you can basically do some simple design of the piping system. Design is to design the diameter, what type of diameter of pipe you're gonna use for that system. Okay.